when night falls and you are strolling through the dazzling city streets, looking up at the sky lit by neon lights, or standing in the dimly lit countryside, gazing at the vast and profound starry sky. Have you ever wondered about this? Behind those distant points of light, could there also be life? And where are they? In 1950, on the way to lunch with colleagues, the famous physicist Enrico Fermi suddenly posed the same question: where is everybody? This simple inquiry later became known as the Fermi Paradox. Given the billions of stars in the Milky Way and the mathematical probability of billions of Earth-like planets, advanced civilizations should have appeared long ago. Yet, why do we see no trace of them? Another famous astronomer, Carl Sagan, offered a more romantic perspective. The universe is a pretty big place. If it's just us, it seems like an awful waste of space. He believed life is a natural expression of the universe. Our existence is not an exception, but rather a cosmic inevitability. So in 1990, the Hubble Space Telescope became humanity's first set of eyes for observing the deep cosmos. In orbiting the Earth, it bypassed atmospheric interference, allowing us to witness the grandeur of the universe with unprecedented clarity. It sought to peer through the dust, looking back at the dawn of the universe's creation. It analyzed the atmospheres of distant planets, searching for evidence of other companions existing or having once existed in the cosmos. Today, this heavy responsibility has been entrusted to its successor, the James Webb Space Telescope, JWST. The vision for the James Webb Telescope dates back as early as 1996. After numerous delays and budget evaluations, it finally launched on Christmas Day 2021 aboard an Ariane 5 rocket. Following a month-long deployment and calibration, it successfully reached its intended orbit, 1.5 million kilometers from Earth. In mid-2022, it officially began scientific observations. The James Webb Telescope is equipped with a 6.5-meter gold-coated primary mirror, making it the largest space telescope in human history. Its signal-gathering capability is 6 times that of Hubble. Primarily observing in infrared, it can peer through cosmic dust to see the earliest moments of star and galaxy formation. To prevent solar heat from affecting its sensitivity, it carries a 5-layer sun shield, which when unfolded is as large as a tennis court. It is also equipped with an active cooling system to maintain the instruments at temperatures near absolute zero. This system is complex and exquisite, like a flower blooming in deep space, embodying the pinnacle of human engineering in cosmic exploration. Since its deployment, the James Webb Telescope has returned many images never seen before. From the magnificent cosmic cliffs in the Carina Nebula, to the intricate orbital dance of Stephan's Quintet and the vibrant remnants of the Southern Ring Nebula, as well as countless distant and mysterious new galaxies, the cosmic tapestry has never been unveiled before humanity in such high definition. Meanwhile, James Webb also bears the mission of searching for extraterrestrial life. Its mid-infrared instrument, MIRI, possesses extreme sensitivity and spectral resolution, specifically designed to analyze chemicals in distant atmospheres that might be linked to biological processes. How do we know the composition of a distant planet's atmosphere? The answer is hidden within light. The sunlight we see daily actually contains a wide spectrum of wavelengths. When you decompose light using a prism, you see a rainbow-like spectrum. Different molecules absorb light at specific wavelengths, leaving unique fingerprints in the spectrum. In exoplanet research, a key observation method is the transit method. The rare transit of Venus that occurred in 2012 was when Venus happened to pass directly between the Sun and the Earth, casting a small dark spot on the Sun's surface. Similarly, when a distant planet passes in front of its host star, the starlight passes through the planet's atmosphere before reaching Earth. In this moment, The universe performs an experiment for us. We only need to search for the fingerprints left by various gases in the observed spectra to confirm their existence light years away. MIRI is the instrument that deciphers these fingerprints. Operating in several mid-infrared wavelengths, it can capture absorption features of key molecules like methane, carbon dioxide, water, and ozone. Through high-precision spectral analysis, faint changes in starlight allow us to infer the planet's atmospheric composition, temperature structure, and even possible climate mechanisms. Among many exoplanets, one planet stands out particularly. It is called K2-18b, located in the constellation Leo, about 120 light-years from Earth. This planet has a mass about 8.6 times that of Earth, but is only 2.6 times Earth's volume. It orbits a red dwarf star, smaller and cooler than the Sun, and resides within that star's habitable zone, the region where temperatures could allow for liquid water. Because of this, K2-18b has long been considered one of the most promising candidates for life. In 2023, using near-infrared observations, JWST first detected methane and carbon dioxide in the atmosphere of K2-18b. This marked the first time humanity discovered carbon-based molecules in a habitable zone exoplanet's atmosphere. These findings hint that the planet may possess the necessary conditions for life. Even more excitingly, in a paper published last April, MIRI, observations of K2-18b's atmosphere suggested the possible presence of dimethyl sulfide, dimethyl disulfide, and other sulfur-bearing organic molecules. These molecular names might sound unfamiliar, but on Earth, they are produced almost exclusively by phytoplankton in the oceans. When these marine microorganisms die, they release dimethyl disulfide, which is then broken down by bacteria into dimethyl sulfide and other byproducts. This process is extremely active in Earth's surface oceans, leaving distinct traces throughout our own atmosphere. Because of this, they are currently considered the closest chemical evidence to a signal of extraterrestrial life. Beyond its chemistry, K2-18b's physical environment also mirrors Earth in several remarkable ways. The red dwarf star it orbits, K2-18, has an extremely long lifespan and stable energy output, providing a lasting window for life, gradual evolution. Furthermore, K2-18b appears to have a sufficiently thick atmosphere to provide a temperate and stable surface environment for life to form. Of course, science is always cautious. In the latest observations of K2-18b, the statistical significance stands at 3.4 sigma, meaning there is a 99% probability that the result is real. However, this has yet to reach the 5 sigma standard required for a confirmed discovery in astronomy. In other words, the spectral signatures of dimethyl sulfide still require more data for validation. Whether they truly originate from biological activity needs multifaceted evidence. We cannot deny the possibility of life simply due to a lack of conclusive proof, nor can we assert we are not alone based solely on the presence of certain molecules. As Carl Sagan famously said, extraordinary claims require extraordinary evidence. Perhaps, even in our entire lifetimes, we may never hear that cosmic echo from the universe. But this inquiry is profoundly meaningful in itself. In the journey to find other lives, aren't we also re-examining ourselves within the universe? If you like our video, please like and share, and feel free to tell us your interested areas in the comments. If you are also a researcher and want to share your work with others, please contact us. Follow us and welcome to Spinach University.